Hello and welcome to another mini lesson about formal language theory. In the last lesson we talked about how we can formally define a finite automaton, a deterministic finite automaton. In this video we're going to talk about how we can formally define what we're doing when we walk through the steps of an automaton, right? So far we've been able to sort of point and describe what we're doing when we go through one of these systems. In this video we're gonna talk about how you can write out the steps like you're doing a proof, so that you can show that you're really going through the steps all in the right way. Alright, so in order to do that, we need to first define something called a situation, which basically tells you how far you are through the automaton, right, at any given moment, at any given step in your proof. Right, so as you take a step, you enter a new situation. Every time you take a step, you enter a new situation. So a situation is a triple. So it's an X, a Q, and a Y, where X is the portion of the string that's already been processed. Q is the current state that you're in, and Y is the portion of the string that's left to be read into the system. So if I feed this A, then if I feed it this string ABB, right, the first step, the first situation that I'm in, I've read nothing into the system, right? Nothing has been read in yet. It's an empty string. That's our symbol for the empty string. Remember that. And I'm sitting here in Q0, which is the current state that I'm in. And this is the portion of the string that still has to be processed, ABB, right? So that's how we describe a situation. When we want to say that we're moving from one situation into another situation, we use this turnstile symbol. That's what the name for this symbol is. You'll see it when you read the book, exactly what it looks like. It's a little hard to draw out, so it really looks correct. And what this means casually is that within one move you make it to this other situation, right? That's approximately what it means, is that if I'm sitting here in this situation, within one move I can be in another situation, right? I haven't specified that yet because we're going to go through that step by step. But if we're going to formally define how we do this, we're going to give our formal definition here. So if we have a deterministic finite automaton M, which just has all the pieces that a deterministic finite automaton has, and we know that we are in a situation that's defined as a triple of X, Q, and Y. We know that within one move we are in a situation X prime, Q prime, Y prime, if and only if the first condition says there is a symbol that is a member of our alphabet, right? Such that Y, the portion of the string yet to be processed, is made up of that symbol and whatever Y prime will be, right? So whatever will be the unprocessed portion in the new situation, and X prime, which is whatever will be the fully processed portion in the new situation, is made up of X, which is the part we've processed already, followed by this symbol, right? So that's our first condition. This will be if this isn't quite clear to you yet exactly what that means, it'll be clearer when we walk through an example. But it basically means we're just going to take one symbol of the alphabet and shunt it from here into here, right? So that basically means we're processing one symbol. That's basically all that this step means, is process a symbol. And the second condition says that our function here, which tells us what's connected to what in our automaton, when we take the function of Q and this symbol, it'll end up at this new state, right? So it just basically means there's an arrow labeled with this symbol that takes us to a new state, right? So this says process one symbol, and that symbol takes us to the state in this triple, right? All right, so let's go through this this particular statement step by step and show how we would prove it. Now, because of space here, we're going to do it up and down, but you can do this side to side too. You can just put the turnstile here and then put the next state over here, and that's how they do it in the book. I just don't have room here to do that. So just be aware that a lot of times when you see a proof like this, it'll go from the left side to the right side. I just don't have room to do that here. Okay. So we've already talked about how this is our starting situation. When we drop in with this string, this is our string that's yet to be processed. This is the start state that we drop into, and this is an empty string. We haven't processed anything yet. So what can we do when we're building our next situation? So what do we do to move one move? So we want to move to a situation x prime, q prime, y prime in one move, right? So we take a symbol that is a member of the alphabet, such that the part that we've processed so far is made up of that one symbol and some other string, right? So if we look at our string that is yet to be processed, it's made up of one symbol A and then another string, right? That's going to be our symbol. And we also have to make it so that our new x prime is going to be whatever we have in x so far, followed by that symbol. So whatever we have in x so far is nothing, right? And so if we follow this up with nothing, or with our one symbol, it's going to be A. That's the part that we've now processed completely. And so now we have our x, and then we also have our y prime, which is going to be B, B, A, B, right? That basically says we've read one symbol. But now we have to figure out what our q prime is going to be in our new state. So we go to our function and we find out if we are in Q and we want to add that symbol, what state do we go to, right? What state do we end up in? So if we are in Q0, because this is our starting Q, and we want to add the symbol here, A, what state do we end up in? We end up in Q0, right? So that is how we use this definition to walk through these steps. We're going to just do the rest a little more informally rather than going back to this definition for every little piece. And we're going to read through this thing. So what do we do to build our next state? We're going to read one more symbol. So we take this and it now becomes AB, comma, and then we know that we're in Q0, right? And we're going to read a B. So we're in Q0, we're going to read a B that ends up in Q1. And we've read a B, so we now just have Bob, B-A-B, in that portion. And now we put another turnstile because we're moving on to another step. We know that we're going to read one character from here. So this becomes ABB. We know that we started in Q1, and we know that we want to read in a B. And when we read in a B, that's going to put us in Q0, which leaves us with AB on the right portion. And now we do another turnstile. And we're going to read in another character. So we move that character into here. And we check out our function, which we can visualize most clearly here. If we're in Q0 and we add an A, it puts us back in Q0. And since we've read in that character, we're left with just B on this side. And finally, we're going to read in one symbol. Oh, let's do our turnstile. We're going to read in one symbol, which leaves us A, B, B, A, B. And it leaves us with an empty string on the right side. And it leaves us in what state? We're starting here. We're going to add a B. It leaves us in Q1. and success. So how do we know if we've had success with one of these things? We should have a couple things be true about our situation when we reach the bottom, when this is just an empty string. First of all, this has to be empty. We have no string left to process. We've got nothing left to break apart. Second of all, this has to be a member of your F for your deterministic automaton. So that means that this has to be an acceptable final state in your automaton. And this, just incidentally, we don't really care what's in here, but this will be the string that you read. Right. So in order to start, you have an empty string on the left, you have your start state in the middle, and you have whatever string you're going to read in here. In order to end, you have this string you read on the left, you have your final state in the middle, and you have an empty string over here, and that's what's going to tell you that it does accept it. So I think the example, there's an example given in your book of a string not being accepted, so check out your book if you want to see how that looks. But basically, unless it looks like this, your string is not going to be accepted. So this is a lesson about moving to different places in finite automata. In the next one, we'll start talking about non-deterministic finite automata.